So, hello everyone, today we will discuss about the self assembled monolayers. So, it is basically a route for the chemical modification. So, in the last lecture we discussed various techniques for the surface characterization, basically microscopic techniques and the spectroscopic technique. Then microscopic technique we discussed the optical microscopy, electron microscopy, atomic force microscopy. Similarly, in the spectroscopy techniques we discussed the photoelectron spectroscopy, then X-ray spectroscopy, infrared spectroscopy. So, in today's lecture first we will discuss a brief about the chemical modification route, that is the formation of self assembled monolayers. Then we will see how we can characterize the modification process to study the kinetics of self assembled monolayers or kinetics of surface modification. So, as the name suggests, this self assembled monolayers. So, it is a highly oriented and ordered 2D molecular arrangement over a surface. So, basically these monolayers are self assembled monolayers, they are formed over a surface and they are highly specific toward the substrate, and as the name suggests, self assembly means it is a spontaneous process through which this formation of self assembly takes place, and it may also be the covalently linked on the surface. An important thing with the self assembled monolayers is it is a chemical route and it does not affect the bulk property of a biomaterial. So, this is the very positive thing about this, that it does not affect, does not deteriorate the bulk property of a implant biomaterial. So, I will quickly go through the historical perspective. In 1946, Zisman et al. Introduced the term self assembly, and in 1980, Sanjeev et al. He showed the formation of a self assembled monolayers of organosilane on a silicon surfaces, and as you know, the self assembled monolayers means the name suggests the ability to assemble themselves spontaneously into monolayers. So, the ability to assemble themselves means spontaneous assembly or arrangement in form of monolayer on a surface, that is the self assembled monolayers. Now, this is a structure, or you can say how the self assembled monolayers look like. So, let us say you are having a metal substrate. So, in the metal substrate it is having, this is the interface, and at the interface you will have a some functional group slash reactive groups. And now, let us discuss about your surface modifying agent. So, this is your surface modifying agent from here to here. So, it is again going to have a head group, and this head group is going to interact with your surface functional group. So, here there will be the interaction between the top layer of the surface and the head group of your surface modifying agent. It is also having a spacer or a chain which will decide what will be the length of self assembly. So, it will decide the length of the self assembly, or you can say the thickness of the this monolayer. and at the top it is having a terminal group, and the terminal group will decide the what is its functional group. For biointerfacial interaction. So, basically once the surface is modified, it means the terminal group is going to interact with the, this is your terminal group, it is going to interact with your body fluid. So, basically these terminal groups determine the surface property and the chemical functional group. It means what kind of this protein surface interaction or the cell surface interaction will take place, that will be decided, or you can say regulated by this terminal group in case of modified surface. Now, this spacer length, it may be in the range of 1 to 3 nanometer. It will vary depending on the modifying agent. So, this is the overview of a self assembly. Now, the interaction between this substrate and the surface modifying agent, it may be the physioadsorption, it may be the chemical adsorption, or it may be some other interactions. So, in case of physical adsorption, it means typically it will have the van der Waals forces, and in this case the enthalpy will be less than 10 kilocalorie per mole. Chemical adsorption means typically the formation of covalent bond. So, this is much stronger, and this delta H will be higher than 10 kilocalorie per mole. Other interactions may be the hydrogen bonding or ion-ion interactions. So, here I have shown two expressions. First is your surface, and this is your surface reactive group. This is your surface modifying agent. So, here this is a terminal group, and this is the head group. So, now this surface reactive groups and head groups are going to interact, and basically this is like a SiO Si. So, this CH3O and H. So, it is like a condensation reaction. So, it is like a condensation reaction, and this R1 is the terminal group, which is going to regulate the chemical functionality of the modified surface, and this is the formation of a covalent bond. So, this is one example. So, basically on the silica or glass surface or oxide surface, this oxide surface is first hydrolyzed to have the abundance of OH group, and then this OH group reacts with the head group of a surface modifying agent to have a covalent linkage, and at the end it is like a condensation reaction. So, CH3OH, it depends on the what is the head group. So, that the product is out, and this R1 group will decide the surface functionality or the surface wettability of a modified surface. In case of surfaces having the SH group, particularly in case of gold, we are going to use the thiol coupling agent, and this one is known as the silane. This is the silane coupling agent, silane, and this is a thiol coupling agent. So, it will have the RS, this H group will go out from here and this S will bind to the gold surface. So, here is the formation of the surface modified group, hydrogen is coming out from here. So, here again we will discuss, let us say this is the organosilane, that is what I discussed, it is another representation. You are having a oxide surface here. If you hydrolyze this, oxide is now converted to the OH. Now, this is your surface modifying agent, or you can say a silane agent. So, this head group is going to react with the OR is going to react with the OH. So, here one ROH will be out and this SiOSi new covalent bond formation is taking place, and this X group is now will be the surface functionality. So, it is a covalent attachment on hydroxylated surface, and the formation of strong siloxane bond SiOSi takes place at the surface outer layer, and the X dictates or regulates the surface functionality or surface wettability. So, based on the type and the reactivity of substrate, the ligand terminal group is altered, and depending on the terminal group and depending on the head group, if you change the terminal group, you are going to change the functionality. If you are going to change the head group, it means you can apply it for the different surfaces, like for the silica surface you are going to have the silane head group, for the gold surface you are going to have the thiol head group, and for the metal oxide you can also have the catechol head groups. So, here you can have the silane for the silica surface, thiol for the gold surface, and catechol for the metal oxide surface. In all the cases, whatever is the X, it will decide the surface functionality. So, for a given surface, we have to choose which type of surface modifying agent is required. So, here again I have listed the same thing. For silica surface, we go for the silane group. For gold surface, we go for the thiol or dialkyl sulfide groups. For metal oxides, we go for catechol groups. For glass, gold and metal oxide, one can also use various polymers or macromolecular polymers, because polymers also have various surface functional group which can either physically or chemically adsorb on the surface. Now, here this is the effect of, or you can say the influence of terminal group. So, if you are having only R1, only one terminal group, so it is called a single or mono self assembled monolayers. Like here on the gold surface, you are having all X groups. So, it is called a formation of mono SAM. Now, on the gold surface as we discussed, you can use thiols, we can also use dialkyl disulfides. So, basically the S bond is there between the S bond is there between the surface and modifying agent, and here is the X group and this is the surface. Now, in case of mixed SAM, as the name suggests, there should be at least two different surface terminal groups. Here I am listing R1 and R2. So, what is happening here? You just see, this is R1, this is R2, again this is R1, this is R2, this is R1, right. even the same molecule like dialkyl disulfide may have different R1 and different R2. So, in this way we mix the two different surface modifying agent which are having different terminal groups, and they are applied for the formation of self assembled monolayers to form the mixed SAM. So, it means here we are tuning again the surface functionality, because if you are using the mixed SAM means the wettability or the surface functionality will be between the R1 and R2, and that will vary depending on the ratio of R1 and R2. So, here the things will be decided what is the ratio of R1 and R2 on surface. So, for further detail this we can refer the self assembled monolayers in biomaterial. This is a book chapter. Now, for the preparation of the SAM we can use this Langmuir Blodgett. So, basically their ionic electrostatic interaction take place, and these are the molecules. You can use the alkyl acids or other molecules, and these are the substrate. We can use metal oxides or polar or ionic surfaces. So, here the interaction is this ionic or electrostatic interactions, and the interaction energy or bonding energy is 50 kilojoule per mole. Now, in case of self assembly, if you are going for the thiol coupling agent, so for thiol you have to choose the, or you can say thiol can be applied on the gold, silver and copper surfaces. So, in case of thiols the bonding energy is 177 kilojoule per mole, but if you are going for the selenization, then we are using the silane, and it can be applied on a silica or the oxide surfaces, and here there will be again covalent bond formation SiO or SiC, and here the bonding energy is the highest among them. So, we can see here that if you are going for the selenization particularly, then the bonding energy will be the highest, and accordingly the stability of modification will be improved. So, depending on the bonding energy it decides the what is the stability of that particular modification, because of course after modification whatever the terminal group is there that will decide its functionality, but if it is not stable it means with time it may be removed. So, this particularly in case of self assembled monolayers as it is a covalent link. So, these surfaces are much more stable as required for the physiological applications particularly in case of biointerfacial interactions. So, now we will quickly discuss what are the different factors which affects the formation of self assembled monolayers. So, as we have seen it is a condensation reaction. So, the presence of water may interfere the reaction between the surface functional group and the surface modifying agent head group, right. So, we are having the reaction between the surface reactive group plus head group of modifier, right. So, as the head group of modifier is also reactive, particularly if you consider this methoxy group or ethoxy group. So, in presence of water molecule this polysiloxane bond formation may take place. It means two silane molecules themselves react with each other to form the polysiloxane bond. So, in this way we have to particularly, if you go for this surface modification, we have to see what is the requirement of moisture, and in case of sealant mostly it is done under the inert atmosphere. Now, effect of temperature, as you know, this is a chemical reaction. So, if you increase the temperature, it is going to increase the rate of reaction. So, we call a temperature the threshold temperature, which is required for the formation of complete self assembly. Tc, it is related to the what is the length of the alkyl chain, and if you go temperature above the Tc, the monolayer formation is inhibited, and it may also yield a very dense packing on the surface. Apart from this concentration of modifier. So, basically it is like a chemical reaction. So, if you change the concentration of the reactant, it is going to affect the rate of reaction. Again the choice of solvent, the solvent should not react with the substrate, it means it should be inert to the substrate, at the same time it should solubilize to the surface modifying agent, and again what should be the moisture. You may have to go for the anhydrous solvent as well, and of course this reaction time, as it is a chemical reaction. So, depending on the reaction time, a reaction will reach to its equilibrium. So, these are the factors: the moisture content, temperature, the concentration of the modifier, and in fact the concentration of your surface reactive groups also matter. Concentration of surface reactive groups, and choice of solvent, and reaction time. So, next we are going to discuss here the kinetics of the attachment and reorientation of a particular sealant that we have chosen is the octyl. This is the 8 carbon octyl triethoxy OCH3 ethoxy O CH2 CH3. So, you are having CH3 2 whole 6, then again CH2 attached to the Si, and this Si is attached to the O C2H5 O C O C2H5 O H5 C2, right. So, this is the ethoxy group, 3 ethoxy group here Si, and this octyl means 6, 7, 8 carbon chain, right. So, here we are going to see how its attachment and reorientation takes place. So, particularly we are interested in the its kinetics part, because if I see the literature, there is a lot of ambiguity, particularly in terms of reaction time. So, it varies between the few minutes to the 24 to 48 hours. So, the objective of this work was to analyze the kinetics of the self assembled monolayers, particularly this was the a model coupling agent or model surface modifiers was chosen. So, as we have chosen the silane, so the surface was also selected as a silica surface, and now here R group is octyl group here. So, it tunes the surface chemistry as well as the surface hydrophobicity or the wettability. So, as I discussed, then it is having a C2H5 ethyl group OR. So, it is ethoxy group, it is a covalent bond formation. So, what covalent bond formation is taking place here? It is a Si O Si, right. So, with time more number of bonds of SiO will take place. Now, if I go here at the same time the SiOSC its bonds should be decreasing because it is getting hydrolyzed, right. So, there should be decrease in the SiOC, this bond is removed and SiOSi is formed. So, now we will see how we can study how we can apply the surface characterization techniques to study the to investigate the formation of self assembled monolayers. So, it is hypothesized that this is your surface and these are the surface modifying agent. So, initially they will be randomly organized on the surface, they will come like this, it will be we say in the lying down phase. Then after that they will try to form small patches or small islands. Then with time there will be infilling and there will be formation of a complete SAM. Now during this infilling there may be also the rearrangement of the pre-attached or pre-adsorbed surface modifying agents. So, we are assuming two steps here, a silica surface sealant, the first step is its attachment and second step we are considering as a rearrangement. So, here the rate constant is K1 and for the second step the rate constant is K2. So, this is very much similar SiO R1 what we discussed the same salinization kinetics and here it is just a rearrangement, right. So, here R2 means it is not R2, R2 means it is like a R1 dash, it is just a reorientation. So, here we are writing starts with R dash, it is going to R1, it is going to R2, but this R1, R dash and this R2 all are the same terminal group. R dash, R1, R2 they are the same terminal group. It should not be confused with the mixed SAM. So, this experiment was performed. So, this is your reaction mixture which is having a surface and the silane agent. It was performed at 37 degrees centigrade in the inert atmosphere like nitrogen and the solvent was the anhydrous toluene. It was performed in the vacuum. So, after that surface modification at different time intervals, we can analyze the surface roughness using the AFM. We can analyze the surface wettability or contact angle using goniometer. The surface thickness can be analyzed using the ellipsometry and surface functional group is analyzed using the FTIR spectroscopy. So, here I am presenting the FTIR spectroscopy. So, as we discussed there should be formation of new SiO bonds. So, you just see the peak intensity in the FTIR is increasing which correspond to the SiO it is around 1045, but at the same time at the time 0 we had a peak around 1080 which correspond to SiOC bond which is getting completely removed from here. It means the head group is getting removed or condensed, at the same time SiO bond formation is taking place at the surface. So, at the same time we know that the peak area is proportional to the abundance, area is proportional to the so if you try to plot the peak area with time. So, we should observe a increasing trend. So, what we did, we are plotting the peak area with time here, right. The normalized absorbance you are plotting, and by seeing the nature of red dots are the experimental data. So, these experimental data were fitted with the exponential association functions, and it was fitted with minimum 2 exponential functions. It means the minimum 2 number of different steps are involved. So, it was fitted with the 2 exponential functions. So, the first exponential, it is very fast, you can see here this purple line, it is very fast and reaching to plateau, and second exponential function is starting slowly and it is continued for a longer duration. So, we confirm from here that there are 2 steps. The purple line we are referring as the attachment, it is a quick step, and the reorientation part, that is a slow step. So, from the experimental data, if you fit this experimental data with the exponential association function, so we will get the value of k1 and k2. And this k1 and k2 will say what is the rate constant and how long it will take the formation of 100% self assembly. Now, again we also measured the water contact angle. So, here again you just see what is the contact angle of your clean silica surface or glass surface is, it is less than 20 degree, and the contact angle of the pure octile surface is theta of octile is about 100 to let us say 102 degree. So, with time what is happening? Contact angle is increasing and reaching to a plateau value. It means the surface energy is changing with time, and this surface energy will be the function of what is the fraction of this silica group is there, or what is the function of your blank surface, and what is the fraction of your octile surface. So, the total energy will be the sum of O refers here is the octile and B here refer is the blank or a clean surface. So, as I told the theta 0 is complete case 102 and this is less than let us say or 17 or 18 something like that. So, any time the contact angle is the sum of what is the fraction of octile group is present and what is the fraction of your blank surface, and F total fraction will always be 1. So, if you have measured this contact angle with time, then from this contact angle data we can find what is the value of O, means fraction of octile group on the surface, and we have calculated this and plotted here. So, what we found is the fraction of octile coverage is again increasing with the time and it is reaching to plateau. It means at this point it is a 100% octile group, 100% FO. So, what we did here, again we applied the same K1 and K2 which we got from the FTIR data. We applied same and K1 and K2 and you just see the dot points are the experimental data and black line is the fitted data. So, again with the same K1 and K2 these experimental data are very well fitted. So, it again suggests that it is having the minimum 2 steps, attachment and the reorientation, and it also suggests that kinetics of the SAM formation can be analyzed either from the FTIR data, also we can analyze using the contact angle data. Now, next we can also analyze using the atomic force microscopy, which gives information about the surface coverage. So, here you can just see with increase in the time there is a increase in the surface coverage, and this 0 minute, 1 minute, then this is a 4 minute, 8 minute, 16 minute, then 60 minute, F is 60 minute, G is 90 minute, and H is 24 hours. So, what it says is with increase in the time you can see there is a formation of the small islands, it looks like a small patches, and then there is a filling up, and after the filling up we can see the grain size or the particle size are also increased here. So, it looks like first there is a filling up, then there is a reorientation. From these images, this is showing a line profile of this particular line here. So, it says how this height varies with the x direction. So, this height was coming out to be in case of few nanometer, and this nanometer it corresponds to the height of the modifier aging. So, whatever this octyl sealant we have used, whatever the height was the alkyl chain was present, that should correspond to the this height profile. So, if you calculate from this image analysis that what is the surface coverage with time. So, here this will be the 0% and this will be the 100% surface coverage in 24 hours. Then here what we did, we this normalized surface coverage from this green dots are showing from coming from the FM data. So, here I have plotted all three, this AFM data, FTIR data and the contact angle data. So, you just see with time the all three data are almost following a similar trend. It means the kinetics of SAM formation can be analyzed using the either of these data. And what we observed here is it is having a fast process of the attachment followed by a slow process of the rearrangement. So, first process is completing around few minutes, let us say 15-16 minutes, and the slow process is continuing up to 8.5 hours. Still this particularly for this case 24 hour is not required. So, this was the formation, or you can say the kinetics of the self assembled monolayers. So, now how we can further apply for the biointerfacial interaction is we can change the surface terminal group. So, we can make the hydrophobic surface, we can prepare a hydrophilic surface, also we can prepare a moderate hydrophilic surface, or even we can prepare the mixed SAMs. And as this surface chemical group is changing, chemical functionality is changing, this means surface energy is also changed. It also surface energy also depends on the packing of the silent molecules, means what is the thickness of particularly that thickness of the modified layer. Then we can tune the surface charge. So, this surface wettability, surface energy, surface potential are again surface roughness. So, here by simply using one technique, the formation of SAM, we should be able to tune wettability, surface energy, surface charge and surface roughness, or you can say these properties are also interconnected and depends on the which modifying agents we are applying for the surface modification. So, here I am listing that this particularly this amine propyl triethoxysilane was used, which is having the terminal group of amine group. Triethoxyactylsilane was used, which are having the terminal group of CH3 group or octyl group. We can also use the mixed SAM of this APTES and TOS, and also we can form the COH group. So, as expected, the water contact angle of amine is 60. For the octyl it is 102 hydrophobic surface, and for the mixed surface it is coming out to be 81. It is again here it is complementing or verifying the Cauchy equation. It should come in between these two depending on the ratio of NH2 and CH3 group present on the surface. And as COH group is the hydrophilic group, the hydrophilicity or contact angle of water is further decreased to the 41. Now, if you want to calculate the surface energy, we can use the geometric mean method as we have discussed in the earlier slides. So, we have to measure the contact angle of that one another liquid. So, here you have used the diiodomethane, this CH2I2 di, and from these two contact angle the surface energy is calculated using geometric mean method. So, you can see this the highest surface energy is coming for the hydrophilic COS surface and lowest is coming for the octyl CH3 surface. And again this surface roughness is also changed. You just see in different surfaces we are having the different surface roughness. So, here by simple surface modification using formation of self assembled monolayers, we have changed the surface wettability, surface energy and the surface roughness. So, here I conclude this lecture. So, today I will discuss what is the self assembled monolayers and how it can be formed on a surface. It is a spontaneous process. It may be through physical adsorption or the chemical adsorption or some ionic interaction on the surface, and what are different factors which affect the formation of the self assembled monolayers. We discussed particularly a case where we studied the kinetics of the formation of self assembled monolayers on a surface, which we found that it has a minimum 2 steps, its attachment and the reorientation part, and attachment part is quick, completes within less than 20 minutes, and orientation part completes in about less than 9 hours. So, in 9 hours we observed that self assembly was completed. So, also we saw that the kinetics of self assembly we can analyze either using the FTIR spectroscopy or water contact angle or the surface coverage using the atomic force microscopic image. Thank you.